Welcome to a pragmatic deep dive into reinforcement learning. Forget the hype. Today, we're treating RL like debugging a complex system, understanding its components, interactions, and bottlenecks. At its heart, reinforcement learning is about learning through trial and error. It's a feedback loop. An agent takes an action in an environment, observes the outcome, both the new state and a reward, and uses this to adjust its strategy for the future. Let's break down the bare metal. The agent is the decision maker, your program. The environment is the world it interacts with, the system it's trying to influence. The interaction is defined by three key signals: state S, a snapshot of the environment; action A, the agent's choice; and reward R, the scalar feedback, a reward for good actions, a penalty for bad ones. This reward signal is the crucial driver of learning. Mathematically, RL often operates within a Markov Decision Process, or MDP. The key Markov property means the future depends only on the current state, not the entire past history. The environment's behavior is defined by P, S, RS, A, the probability of transitioning to state S and receiving reward R, given state S and action A. The agent strategy is its policy, pi, dictating actions based on states. To guide this policy, we use value functions. The state value function, VES, estimates the expected future reward from a state, while the action value function, QSA, estimates the reward from taking a specific action in that state. A core challenge is the exploration versus exploitation dilemma. Should the agent stick with what it knows works best, exploitation, or try new actions to potentially discover even better strategies, exploration? Too much of either can be detrimental. Q-learning is a foundational algorithm that learns action values. It uses a learning rate alpha and discount factor gamma to update its estimates. However, it struggles with large state spaces. Deep Q networks, or DQN, tackle this by using neural networks to approximate Q values, employing techniques like experience replay and fixed Q targets for stability. Policy gradient methods directly optimize the policy itself. Reinforce is a basic example. Actor-Critic methods like A2C and A3C improve this by using a value function, the critic, to help train the policy, the actor. This reduces variance and speeds up learning, especially with asynchronous parallel workers. Where does RL shine? In game playing, achieving superhuman performance like AlphaGo. In robotics, teaching robots complex tasks in dynamic environments. And in recommendation systems, optimizing user engagement over the long term. However, RL faces significant hurdles. It's notoriously sample inefficient, requiring vast amounts of data. Designing effective reward functions is tricky. Exploration in complex spaces is difficult, training can be unstable, and learned policies often fail to generalize to new situations. Looking ahead, RL is evolving towards greater efficiency and better exploration. While it's becoming a powerful tool for specific optimization problems, it's not a universal solution. Think of RL as a highly specialized processor, incredibly potent for certain tasks, but not the main engine for everything. Thank you.